Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, what data is most useful? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week we're returning to the topic of self-driving cars. I'm finding out how machine learning is helping robo-taxis understand and anticipate the behaviour of other road users. Before we get started, don't forget to subscribe to Robot Talk on your favourite podcast provider to make sure you're the first to hear the latest episodes. Another way to find out about new episodes is the email newsletter, which you can sign up to by going to robottalk.org. I'd also like to let you know that I'm currently offering a 50% discount on your first month's membership to the Robot Talk community on Patreon. This is a fantastic chance to try out the awesome member perks at a discounted price. Just go to patreon.com/Claire Asher and use the code WINTER25 for a new paid membership by the 24th of December. So, with all that said, let's get on with this week's interview. I recently had a fascinating chat with Shimon Whiteson from the University of Oxford and Waymo about machine learning for autonomous vehicles. This week, I'm speaking to Shimon Whiteson, a professor of computer science at the University of Oxford and senior staff research scientist at Waymo, working on machine learning for autonomous vehicles. Hi, Shimon. Wonderful to have you on Robot Talk.
Hi, thanks for having me.
Your research is focused on a type of artificial intelligence called deep reinforcement learning. So for listeners who might not be familiar with that, can you briefly explain how deep reinforcement learning works?
Sure, I'll do my best. So at a high level, reinforcement learning is a type of machine learning. Machine learning means the computer is learning from data. So instead of programming it with a bunch of rules, we just give it examples and expect it to work out the rules from the examples. Mm-hmm. There are many kinds of machine learning, and you can kind of view them on a spectrum in terms of how strong is the feedback that we give to the computer while it's learning. So at one end of the spectrum is supervised learning. So this is learning from labeled examples, like you want the computer to identify which images have cats in them. You give it a bunch of images. You tell it which ones have cats in it.
Yeah.
So you're supervising the learning process with these like examples of the correct answer. And then at the other end of the spectrum, you've got unsupervised learning, which is like you just have a pile of data and you throw it at the computer and ask it to find patterns or like estimate the distribution that the data came from. There's basically no labels, no supervision at all. So reinforcement learning is somewhere in between these two extremes. Mm-hmm. You do have some supervision in the form of reward. So you get this reward signal when the computer takes an action. It gets feedback, like a positive or negative reward, telling it how good that action was. Mm-hmm. But this feedback is fundamentally weaker than the feedback you would get in supervised learning. Yeah. Because in reinforcement learning, you never tell the computer what the right answer is. You just basically rate its performance. And it has to learn through trial and error what are the right actions or sequences of actions so as to like maximize this reward signal and behave in an optimal way. Mm-hmm.
Why does this sound like training a dog?
I think that's actually quite a complicated topic, but I think one of the modes of learning that animals and humans use is reinforcement learning, because it is learning through trial and error. I think animals also learn through imitation, so there's a bit of nuance there.
Sure.
But so that's reinforcement learning. Deep reinforcement learning just means that the computer that's learning from this feedback, everything that it's learning which in the case of reinforcement learning would be a policy. That's like the rules that control its behavior, value functions, which help it predict the consequences of its actions, and models, which like predict how the world works. All of these things are represented as big neural networks.
Okay. And so, at the end of all of that, how much do you as the researcher understand about how the algorithm is coming to the answers that it's coming to? Is it completely a black box, or do you have any understanding of what is actually going on?
The reinforcement learning algorithm is typically not a black box because it's typically something which has been designed by humans. Mm-hmm. The thing that the reinforcement learning optimizes, so like the neural network that it's training, that is pretty much a black box. How black that box is depends a bit on the details. So, for example, you can train a neural network that just directly represents a policy. So it maps like inputs to outputs. And then what goes on inside that box may be a total mystery. But there are also reinforcement learning algorithms that instead of directly learning the policy, they first try to learn a predictive model. And then they use that predictive model to figure out how to act. And then there may be some greater degree of interpretability.
Okay. So your involvement with Waymo began in 2019 when they acquired the spin-out company that you co-founded, Latent Logic. So can you tell us a bit about Latent Logic and how it has helped to accelerate Waymo's progress?
So the way this all started, it actually started before I even was in Oxford. Before I moved to Oxford, I was at the University of Amsterdam. And when I was there, I was leading a scientific project funded by the European Union that involved like 6 different countries and different universities and companies. And it was about telepresence robots. So we were trying to give telepresence robots some social intelligence so that it'd be easier for humans to like participate in conversations remotely. And the core tech behind the telepresence robot was imitation learning. So this is not reinforcement learning. This is learning by imitating the correct behavior of human experts. Yeah. So we were like looking at how humans would control the robot manually and then trying to use imitation learning to automate some of that behavior. So when you're using the robot, you could just focus on the conversation without having to worry about eye contact and body language and so on. Mm-hmm. So when the project ended, we thought, maybe this imitation learning technology, maybe it can be commercialized. And we started looking around for like, what would be the killer app for imitation learning? And that's when we started looking into self-driving. So we thought, maybe we can learn driving policies from imitation learning applied to examples of humans driving on the road. Mm-hmm. That was kind of the first idea. But then we realized, and we got some sort of skeptical feedback from venture capitalists that like, well, human drivers might not be trustworthy. They might be reckless. They might be inattentive and so on. So we might not want to imitate their behavior. So it was actually a small step from that to what we ended up doing in Latent Logic, which is training behavior models not to control the self-driving car, but to imitate the behavior of the human drivers that share the road with those cars. So the human drivers, the cyclists, pedestrians, all the road users that interact with the self-driving car, we need good models of their behavior in order to have a realistic simulator. And a realistic simulator is crucial for the testing, evaluation, and ultimately training of self-driving cars. So that was the business model of Latent Logic. We were going to build these behavioral models using imitation learning and then market them to self-driving companies to improve the realism of their simulation tools. Mm-hmm. And this caught the eye of Waymo. I think we were a bit lucky in terms of timing because that was around the time when a lot of self-driving companies, not just Waymo, were waking up to how important it was to take simulation seriously and to build like a really realistic, reliable simulator. Mm-hmm. So they acquired us as part of their effort to do that. So you also asked about how we've helped Waymo accelerate their progress. So actually, we've been quite lucky because after the acquisition, we were able to keep doing almost exactly the same thing that we were doing. Okay. So the team that I lead at Waymo has focused largely on what we call the sim agent problem, so modeling the other road users in the simulator. But we've just been able to do it at like a much larger scale. So Waymo has access to a huge amount of data, huge amounts of compute. And in the time that I've been at Waymo, it has gone through this like exponential scaling process. So when I joined, Waymo was operating in Phoenix and was doing some testing in San Francisco. And now there's like a fully rider-only commercial service available in 5 markets, with 6 more announced for next year. More than 10 million paid rides, hundreds of thousands of miles per week, paid rides on the commercial service. Mm-hmm. And yeah, that exponential scaling has required dramatic improvements in the quality and efficiency of the simulation tools, and we've been able to contribute to that. Since the acquisition, we also took on like another topic, which we didn't work on at all at Latent Logic, but has become one of the core topics of my team at Waymo, and that's on the data curation side. So as Waymo scales up and there's more and more cars on the road, the fire hose of data coming in gets bigger and bigger.
Yeah.
We can't afford to keep all that data. We can't even afford to write it all down. So we have to get smarter about making decisions about what data to keep.
Yeah.
So my team works on building large models that predict, like, if you were to keep this data and then use it later for some resimulation, would something interesting happen? And then we upsample the interesting stuff throughout the data pipeline, on the car, off the car when we're deciding what data to keep, and then even further downstream when we're like selecting subsets of the data to use in like simulation jobs to evaluate new versions of the software. At every step, we have to make smart decisions about what data to keep and what data to use.
Yeah. So what kinds of data is the most useful at this point? The kind of stuff that you really want to make sure you grab hold of to use?
Well, so the fundamental challenge of self-driving is rare events.
Yeah.
So, getting the car to drive well 99% of the time is easy. It's that last 1%, which is hard. Mm-hmm. So anything which could relate to such a rare event is interesting from a data perspective. Now, one of the challenges is that as the Waymo driver gets better, the interesting events get rarer. So it gets even harder to find them. So we are interested in what we call safety-related conflicts. So these are not collisions, because collisions are extremely rare, but safety-related situations that could, if not handled properly, give rise to a collision.
Yeah.
And then those are ones where, like, if we save them and then perform resimulations, in resimulation, we can stimulate counterfactual scenarios to create such collisions and then make sure that we are responding appropriately and so on. So safety-related conflicts are the biggest things. But, there's also things like interacting with emergency vehicles, dealing with situations where the car might get stranded or where there's another car that's stranded, construction zones, where there's like unexpected deviations to the road layout.
Yeah.
All those sorts of things. More interesting than a typical boring bit of data.
Mm-hmm. So as you mentioned, Waymo has very rapidly become the leader in the robotaxi sector. And I've been really amazed by the scale of the operation already, when to me, I'm still living in the world where autonomous driving is very new and exciting and novel. And it's kind of almost mundane for Waymo at this point. So why do you think that Waymo has succeeded where, so many other self-driving companies have failed?
Yeah, it's a good question. So many things about the way self-driving works are kind of common to all the self-driving companies. So there's a lot of ideas that are kind of in the zeitgeist. And, if you look at the academic papers that Waymo has published, the approach and the topics and the themes, they're quite similar to those that are in papers by other self-driving companies. Yeah. There are some things that make Waymo distinctive. So Waymo has been very patient and perseverant. Waymo started in 2009 when it was like a moonshot research project as part of Google X. So it's been like a 15-year path to get here. So that's required a lot of patience and perseverance. If I were to speculate about the strategic reasoning of like the senior leaders at Alphabet, I think they recognized early on that self-driving was going to be a capital-intensive bet. So it requires a huge amount of resources to actually build out these facilities, get the cars on the road, collect the data, build the models, and so on. And, for a big company like Alphabet, a capital-intensive bet is a good one because Alphabet has the deep pockets to show that patience and perseverance where some other players might not be able to. And that's exactly what we've seen in the last, 5 years in the industry, only the strongest players surviving. Another thing that's distinctive about Waymo is a big focus on the multimodal architecture. So as opposed to some companies that are doing a camera-only approach, Waymo is very much focused on a combination of cameras, LiDAR, and radar. And that's been that way from the beginning. Waymo has actually been an innovator in the LiDAR space. And everything we've learned about safety critical systems from other industries for the past 50, 75 years says redundancy equals safety.
Yeah.
So I think the multimodal architecture is key to Waymo being able to offer like a safe, robust product. And like Waymo is very much a safety first company. And that can be frustrating sometimes, internally. Sometimes it's like you want things to move faster or you want to push out cool new things quickly. But Waymo is cautious, possibly to a fault. But that commitment to safety, I think, is important because it is a new technology. And so, building trust with consumers is very important.
Yeah, absolutely.
And, one mistake can cause a lot of damage that's very hard to undo. So that's been, I think, very important to Waymo. And you see that a lot, that like people who've never been in a Waymo often have some skepticism about it. But once you've been in it, it's amazing how quickly it seems normal and how quickly you trust it. So
yeah. So we've had quite a lot of audience questions, so I'm going to start diving into them and we'll see how many of them we're able to get through. So first we had an audience question from Kushatij on Twitter. Kushatij says, what has changed since 2015 to 2020 when full self-driving was struggling to take off?
A lot has changed. So I would say one change is something that doesn't really have anything to do with Waymo in particular, and that's just the deep learning revolution. So the capability of machine learning systems has improved dramatically, and that's in all areas. So, large language models get the most attention. They're not that relevant to self-driving, but certainly vision systems, the entire perception side of self-driving, the sort of core capabilities of the machine learning models that we're able to train has just improved dramatically in the past 5 years. So 2015 was like an eternity ago in deep learning terms. So that's one thing. Something that definitely makes self-driving different from some of the other applications of deep learning is that one of the ingredients for the success of deep learning, which is data, is much harder to come by. So you can just scrape the internet and get a huge data set for training a large language model. But to get data for an embodied system, like a physical system that's actually acting out in the world, that's much harder. And that's where Waymo has a big advantage because we have this like data flywheel, which has been building momentum. So the better our models are, the more cars we can put on the road. The more cars we put on the road, the more data we get. The more data we get, the better our models are, and so on. So getting that flywheel up and running and spinning fast, that's kind of the key. And, if you look at the curve of how many miles per week Waymo has been driving, it's been going up really quickly year on year. And I think that has a powerful self-reinforcing effect.
Yeah, absolutely. So we had a slightly more technical audience question from Sani on Twitter. Sani asks, classical path planning algorithms work well in static environments, but do you think they are enough for the unpredictable real-time conditions of self-driving cars? And for the benefit of me and many of the listeners, can you also please explain what classical path planning algorithms are in your answer?
Well, so first of all, with the caveat that I'm not actually a roboticist, my expertise is in machine learning with an emphasis on reinforcement learning. And robot control is absolutely one of the main applications of reinforcement learning. So I have some familiarity with robotics in that way, but I'm not a roboticist. I'm not an expert on path planning algorithms.
Sure.
But at a high level, path planning algorithms, basically, they're searching through trajectory space. So the robot has a goal or a cost function, and it's trying to find a trajectory that minimizes those costs and achieves that goal by searching the space of possible trajectories. So these are typically what we call open loop algorithms. That means you just plan like a sequence of actions, as opposed to a closed loop policy, which is typically what reinforcement learning would yield. Which like maps states to action. So for every state you're in, it tells you what action you should take in that state. And this can be executed in closed loop. So in closed loop, that means you take into account the things you observe along the way when you're acting, as opposed to setting the whole trajectory in advance.
Right.
So typically, even in classical robotics, these path planning algorithms, they're not enough by themselves, even in a static environment. So they're nearly always combined with some kind of local controller.
Okay.
So the path planning might yield this trajectory, which is like a sequence of states. And then you have some local controller, which figures out what forces should be applied to the different motors so as to cause the robots to travel to like the next waypoint in the trajectory.
Mm-hmm.
And often collision avoidance, dealing with dynamic objects, that sort of thing is handled by these local controllers. So we can think of it as like a hierarchy of abstractions. And the higher you are in the abstraction, the more static things become. Like if you go to Google Maps and ask it how to get to the grocery store, it gives you a high-level route.
Yeah.
That doesn't take into account the fact that, like, when you get to that intersection, a pedestrian might be in the crosswalk and so on. Mm-hmm. Those sort of things have to be handled at a lower level of abstraction. Now, what's often done is that open-loop planning algorithms can be turned into closed-loop behavior using what's called a receding horizon controller. So what this means is you're in a current state, you have some open-loop planner come up with a trajectory, you execute the beginning of that trajectory, and then you see what happens. How did the world respond to that behavior? And then in the new situation, you replan. So you're computing a long plan, but you're only ever executing the first step of it. And then you're replanning to make sure the new plan takes into account anything that happened in the meantime.
Yeah.
And this is also a way of dealing with, dynamic objects and collision avoidance and unexpected things that might come up.
Fantastic. Yeah, thank you for explaining that so clearly. The analogy with like a Google Maps or a sat nav kind of being the path planning algorithm, and then I'm almost imagining like the driver is the local controller who's saying, all right, okay, this is how much acceleration I need to apply to actually make the car do the next action. Yeah.
Yes, exactly.
That definitely makes it easier to understand. And then we had an audience question from Satcha on Blue Sky. So Satcha says, how big is the issue of non-stationarity caused by humans' irrationality? Do the models try to model it explicitly, or do they rely on the sheer amount of data from the interactions? And again, if you could explain what non-stationarity is, that would be great.
Sure. I would actually distinguish here between two related concepts. Okay. So one is stochasticity and the other one is non-stationarity. So human behavior, for example, is absolutely stochastic. That means it's sort of like inherently unpredictable. Mm-hmm. Like the flip of a coin, you don't know, is a pedestrian going to turn left or go straight? So stochastic systems, we have to model them probabilistically. So we have some probability distribution that says, a cyclist who arrives at this intersection from the left side, there's a 40% chance of turning left, a 50% chance of going straight, and a 10% chance of going right. So that's something that's like a distribution that we could model from the data. Mm. But we're modeling the stochastic behavior of the human. Non-stationarity is something different. So non-stationarity means not only is the behavior stochastic, but the distribution from which the behavior is sampled is itself changing over time.
Right. Okay.
Like, yesterday the coin was fair. Today the coin is not fair. Mm. That's non-stationarity because things are actually changing over time. So with this distinction in mind, let me try to answer the question. So human behavior is absolutely stochastic. And this is considered explicitly by Waymo's models at all levels. So it's reasoning in a probabilistic distributional way when predicting other agents' behaviors. This does not imply that those agents are irrational. So the stochastic behavior does not mean irrational behavior. Yeah. Although those humans might make mistakes or they might optimize for inappropriate objectives, like they might care more about speed than safety. Mm-hmm. All those things are captured in that distributional modeling, but it doesn't mean that the humans are irrational. It also doesn't mean that they're non-stationary, because it may be that this stochastic behavior is coming from a fixed distribution. So the stochastic probabilistic modeling is crucial for doing a good job of modeling human behavior without non-stationarity coming into the picture. But non-stationarity can also arise, so traffic patterns may change over time. And Waymo systems also take this into account because our models are constantly being updated. This fire hose of data that I was saying we have to filter through carefully to find interesting stuff, this fire hose of new data is being used to update the models so that they're constantly optimized for like the current distribution of traffic behavior that we see out there. Mm-hmm. And, something that we see more and more often as Waymo ramps up is that we ourselves are affecting that distribution.
Yeah.
So it's more and more common for a Waymo car to encounter other Waymos on the road, or for people's behavior to be affected by the fact that they're interacting with a self-driving car. So we can track those distributional shifts, and we can model humans probabilistically, and then that way we can address both non-stationarity and stochasticity.
Mm-hmm. Yeah, I was thinking as there are more and more autonomous vehicles, and not just Waymo, but other companies who have, slightly different self-driving algorithms, then the behavior of traffic will naturally start to change as less and less of it is being directly controlled by a human driver.
Yeah, so there's a lot of possibilities and implications there. So in the short term, one thing that's interesting for us as machine learning scientists is that when two Waymos see each other, this is a golden opportunity from a data perspective.
Yeah.
So, for example, Waymo has these perception systems that take the raw data that's coming in from the sensors and try to figure out what's going on in the world. Is there a pedestrian in front of the car, for example? But we don't have ground truth. We don't know whether the perception system is right or not. But if there's another Waymo in the field of view, then that gives us like another data source that we can check against. So, for example, we have GPS telling us exactly where that car is. And we can see the other Waymo, from its sensors, it can estimate where that second car is. And then we can compare those to see if they're correct. So from a data perspective, that's really interesting. There are also, in principle, opportunities for like cooperation or coordination, like two Waymos that come to an intersection could communicate directly with each other in order to make sure they navigate the intersection safely. I don't think that's really a priority because basically you want something that navigates the intersection in a robust way, whether the other car is cooperating or not.
That's true, yeah.
So that special case might not be worthwhile. But for example, in Waymo depots, like when the cars come back to the depot at the end of the day, there may be a lot of Waymos navigating a parking lot at the same time. And then that coordination issue becomes much more important.
Yeah, I like the idea of like multiple autonomous vehicles kind of talking to each other. I get what you're saying that in that scenario, it doesn't really make any sense. But I like the idea of it. I guess you could have, if one vehicle encounters a bunch of traffic, it could like give a heads up to the one that's further back down the road, or take a different route. There's been a crash or whatever. There's probably other applications of that. I just like the idea of them talking to each other.
Yeah, so that sort of thing already happens. Like if there's if one Waymo observes that something on the road is not as the map says it would be, because like construction or if a tree has fallen in the road or whatever, an accident, something like that, that information is immediately shared with all the Waymos. So that sort of thing happens already. Okay. Thinking more in the distant future, one thing we see already is that self-driven cars are a lot safer than human drivers. So Waymo recently published a bunch of safety data, and the numbers are amazing. It's like 91% fewer injury crashes, 80% fewer injury-causing crashes, and so on. So in a future where those kind of much safer cars are dominating the road, then you could imagine it might be safer for like cars to drive faster.
Yeah.
Because they don't have this human fallibility to worry about. When I was a PhD student, my PhD advisor, Peter Stone, he had a project, which I personally did not work on, which was about automatic intersection management. Okay. And the idea was that like, if all the cars are autonomous and there's no humans, then they can just coordinate with each other about how to navigate the intersection. And they built this whole coordination algorithm where like, as you approach the intersection, you book a reservation that says exactly which part of the intersection you're going to be using at each like millisecond.
Wow. Okay. Yeah.
And if everyone obeys the coordination algorithm, then like cars can just stream past each other really fast. And, the intersection is like a bottleneck in the traffic network. So if you can make more efficient use of it, it can really improve the entire traffic flow. So the tech has been sitting there for 20 years, just waiting for the real world situation where all the cars can coordinate in that way. Yeah. And, maybe the widespread deployment of self-driving could make that possible.
Yeah. So what are the biggest remaining challenges for autonomous driving?
So first, I would just say self-driving is no longer science fiction.
Yeah.
The technology is here now. It works today as a large-scale commercial product for the general public. So in a sense, we've already done it. The remaining challenges, so one of the ones that I mentioned already, as we drive more miles and the driver gets better, we have fewer hiccups, which means the remaining hiccups are harder to diagnose and address. So we're getting into the even longer part of the long tail. So we have to be even more creative and smarter about how we find interesting things, upsample them, how we simulate stuff that we care about, but which will never appear in our data and so on. So this is, in a sense, a good problem to have. We're like a victim of our own success there. As Waymo scales up, we're increasingly interested in scaling efficiency. So when we go to a new city, we want to reduce the cost of mapping in the new city, of human driving in the new city before we can drive autonomously. So in machine learning terms, we would call this a transfer learning problem. We have a bunch of data from San Francisco, and now we need to drive in Austin. A lot of things are similar, but also some things are different. So how can we positively transfer the useful things that we know and then just minimize the cost of collecting new data to deal with things that are different?
Yeah.
There's also some things so as Waymo scales, we no longer are doing everything ourselves. So in a couple cities, Waymo has already partnered with Uber. And Waymo has announced that when it starts service in Nashville next year, it's going to be partnering with Lyft. And in order to facilitate those third-party partnerships, we have to do some streamlining. So, for example, when a car comes back to a depot, instead of swapping out a hard drive to get all the data, the car just uploads the data over Wi-Fi. So this is something that makes it easier for these third parties to set up a service in a new city. But that means there's a bigger limit on the bandwidth. We can't upload as much data. So then again, we have to be even smarter about which data we want to keep.
Yeah. Shimon, it's been fun chatting to you today. I've been talking to Shimon Whiteson from the University of Oxford and Waymo. Thank you.
Thanks for having me.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. And make sure you check out the awesome new Robot Talk merch that I've created by visiting robottalk.org/shop. You'll find the perfect gift for any robotics fans in your life. Next week, I'll be talking to Oluwami Dosumo Ogumbi from Ohio Northern University about getting two-legged robots moving. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.